So in order to show you the motherboard, had removed the 5 clock bias boards, and I plugged them back in now. You may notice that each clock bias board has its own fiber optic link, which goes down to the fiber optic connectors on the front panel. Right now I've got the science chips are connected to fibers which go over to a rack with ICs in them, and G is here going to my lab computer. I do that because G is the one where it's in your face right here and you can actually see what's going on, so I use G for a lot of things. There are also logical reasons for using G. By default, K is the master, and so if you wanted to use just a single device other than G, you'd have to use K, and of course K is the clock bias board that's all the way in the back, and so it's kind of hard to probe or see what's going on with that one. So all of the clock bias boards are the same. There are just a couple of minor differences in the way we adjust the voltages here on the pot board. So I can give you a tour of this clock bias board, and that applies to all of the clock bias boards. So as I mentioned, the voltages come from the regulator board, and they are I think it's just 5 and 6 in number. Plus and minus 18, which gets re-regulated in several places to be plus minus 15. Plus 36, which is the high voltage that gets regulated to be the output drain voltage, so any voltage above 15 has to come from that supply. Plus 5, which is the voltage that powers all of the logic. So there are 2 sets of plus and minus 15 regulators. These 2 here and these 2 here. Obviously these guys handle more power than these guys. These don't need heat sinks. These guys do need heat sinks. There is then another set of regulators here which are kind of funky. These buffer regulators are not quite rail to rail, so there's one which is minus 1.2 volts to give the low side of those regulators, and plus 6, if I remember, is the other side of those regulators. And then there are 3 additional logic voltages, 3.3 volts, 2.5 volts, and 1.2 volts, and that is all required by the Altera chip, the BGA chip here, which has an internal voltage of 1.2, and then it has 2.5 volt I/O and 3.3 volt I/O. The 3.3 volts is also used for the serial communications device here, the CIRDAS as it's called, which communicates over the fibers through the small form factor pluggable device on the back of the board, and that data link over all the fibers is 180 megabits a second, 12 bits per byte, so that gives you whatever the byte rate is. In addition to the Altera part, the other major component here are these clock drivers. There are 24 clock drivers on the board. They're all pretty much identical. There's 1 or 2 that have special functions, and they are numbered. The small numbers on each one of these driver chips tells you which clock is coming out of which board, and it's just super handy when you're debugging to know where to probe to get which clock. And each one of those clock driver circuits, which comprises a buffer, some analog switches, 2 buffers, nope, 1 buffer, a couple of little tiny analog switches down here. Believe it or not, those are the things that do the work. And then a driver chip, which is actually a DSL driver chip, which has set up to have a gain of 2. And that's important in some applications that you know that's a gain of 2. So you put a volt in, you get 2 volts out of that. And there are actually 2 inputs to each one of these clock driver circuits, a high level for the clock and a low level for the clock. And they're both positive. So there's an input that when you put a positive voltage on it, you get a negative voltage out of the clock. And the other one, when you put a positive voltage in, you get a positive voltage out of the clock. So those are all the major things for clocks. And then you have to be able to generate, you have to select those DC levels. And they all come from 6 precision power supplies, very low noise power supplies up here, 3 negative ones and 3 positive ones. In fact, in KMT, we are only using the 3 positive ones, and we're not using the negative supplies at all because of this characteristic of these clock drivers that they take a positive voltage in one input to make a negative voltage on the output. They're inverting. And in KMT, they're set up for plus 32 volts is the highest one, plus 6 because there are a lot of uses for plus 6, and plus 10. And I'm not even positive plus 10 is being used anywhere. I don't really remember. But those precision low noise voltages and their regulators are actually underneath this pot board, as we call it. Which one of those goes to the 2 sides of the pot is selected with this array of resistors or jumpers, and then you get to adjust each one of the voltages with the pots. So, and they're nicely labeled. For instance, this is pot 1, and it is the one that produces the low level for the serial clocks. The next one produces the high level for the serial clocks. The third one produces the low level for the summing well, high level for the summing well, low level for the reset gate, high level for the reset gate, low level for the transfer gate, high level for the transfer gate, low level for the parallel clocks most of the time, and I'll say a word about that in a minute, high level for the parallel clocks most of the time, low level for the other half of the parallel clocks. The parallel clocks are split in the middle in a section they call A and another section they call D. So this is the clock voltages for the A section, clock voltages for the D section. And then there is a prep voltage. We discovered after we'd put a lot of this together with E2V that it's really required that you be able to take all of the parallel clocks to -9 volts to prepare the CCD to flush it, basically. And so the prep voltage actually goes through 2 clock drivers. The first one selects whether you're going to get the low level selected here by pot 9, in fact, is the normal low level, or if you're going to get the low level selected by pot 13. Since each one of the clock drivers is a gain of 2, and then you go again, and I put a trick in there too, so it's a little complicated what the gains are. I'm not going to try to do that off the top of my head, but these voltages are not strictly a gain of 2 for those specific voltages. And then there are 4 pots for the reset drains, 8 pots for the output drains, and a couple of the output gate, dump drain, and some other electrodes. The final 2 pots here actually aren't used as pots. They're just test points, really. One is ground. This last one is ground, and the other one is the dummy signal, which actually goes down to clock driver 24 to produce the signal that simulates the CCD signal. So that's a quick tour of the clock bias board.